Everybody read chapter 2 already? Oh, we're already starting off on the wrong foot, right? You guys were supposed to read chapters 1 and chapter 2 already. So at this point, you guys should have already read chapter 2. You should know it like the back of your hand. Are you guys ready for a quiz? What? Come on, you guys told me you guys were going to be ready. Right? You ready? Let's go. Oh, he's ready. It's not open book. Come on, you're supposed to know it. Know it doesn't mean you look at the book. Okay, so, but you guys already talked about it. We've already talked about the first part, right? We talked about a physical reaction. We talked about a chemical reaction, right? Good. See, okay, you guys are already on the right foot. We'll see.
Dr. Henry?
Okay, so first off, matter. Okay, so chemistry is just basically the study of matter, right? We think about matter. Everything basically has mass. Do you weigh something? I weigh a whole whopping 220, right? So I have mass associated with me, right? Jessica weighs 110. She has mass associated with her, right? You weigh 155. Do you have mass associated with you? So everything has mass, from the smallest thing to the largest thing, right? So when we think about things, it has mass associated with it. Electrons have mass associated with it. But that we often say that it doesn't. Okay, we'll talk about that a little bit more. Okay, so when we think about things, we think about things in terms of how we see them, right? So I'm a big guy. Can you guys see me? Right? I have a big presence. You can definitely see me, right? So I'm macro. I'm big, macro, right? Macroscopic. You can easily see me with your eyes. Now, something that is small, like let's say a bacteria, can you see that with your eyes? Can you see a single germ with your eyes? Ooh, she got the germ. Can you see it? You guys see it? You don't see it? Come on, what's wrong with your eyes? Right? We can't see things that are micro. I can't see a germ on her, right? I'm lying if I say I do. Am I not? Right? But I can use a microscope, take a little bit of her skin and see, oh, yep, she definitely has a micro bacteria on her, right? I can use a microscope to see it. So we call that microscopic. Then we have particulate. We call particulate those things that we can't see with our eyes and we can't see with a traditional microscope. We have to use special things, like an electron microscope. You guys heard of an electron microscope before? Oh, it's really cool. Electron microscope basically shoots electron particles at something and they bounce off. And the way that they bounce off, they reflect a certain image. Now they shoot electrons. You guys know that an atom is made up of what? It's electrons. What else?
Neutron.
Protons and neutrons, right? Electrons are the smallest, right? They weigh the least. They're shooting that. And so they're using that to image something. And so we can get things that are even smaller than an atom, right? Because an atom is made up of what? Protons, electrons, and neutrons. We'll talk about it more. It won't be on the exam yet, okay? So there are three different things, three different scales, I guess, to take a look at it. We have macroscopic, we have microscopic, and we have particulate, right? Simple? Okay, good. So let's see. If I'm looking at a compound like water, a single water molecule, is that microscopic, macroscopic, or particulate?
Macro.
A single water molecule.
Oh.
Particulate. If I'm looking at a lake, right? It's water. Is that a microscopic, macroscopic, or particulate?
Macro.
Macro, because I can see it with my eyes. Okay? If I'm looking at the coronavirus, is that microscopic, macroscopic, or particulate? It kind of falls in between that micro and particulate, somewhere in between. Okay? Simple? Okay, so now this brings us to a point. Can you guys see a single water molecule? If we look at it under a normal microscope, can we see a single water molecule? Can't even talk to them. No, we can't.
No.
Okay, so often because of that, we need to do something to help us see how those molecules are behaving and how they're interacting and what they look like. So what we do is we make models, right? So this is an example of models. We have here, this is a simple, I'm trying to find it. Okay, there we go. We have a simple stick structure model. This here is methane. Do you guys know where methane is? Harris Ranch is how far from here? 15 minutes away. Harris Ranch is 15 minutes away. So have you guys noticed on Harris Ranch? Not the restaurant. I'm talking about the actual ranch, right? You drive by it. What does it smell like? Can you smell that from here? I know in Kalinga we can smell it. No. No?
No.
Okay.
You can smell the dump. Yeah.
You can smell the dump from here. Okay. Okay, so have you guys have you ever been on YouTube? Anybody use YouTube?
Yeah.
Okay, so go on YouTube and look up fart, right? Fart. 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 F-A-R-T. Fart. Do you guys know what a fart is, right? Everybody knows what a fart is. Guys, you guys act like I said something bad. Okay, so cows fart, right? So cows fart out methane. You fart. Guess what you fart out? Methane. Methane. Most of your fart is methane. So part of that smell that you guys are smelling is that methane. Partially. All of the cows, if you have all the cows in one place, yeah, that could be. And we have a lot more cows today than we had in the old days. And so, yeah, we're kind of helping out global warming a little bit. But damn, they taste so good though, right? Man, a good old oh man, a steak? Come on. Yes. Okay, so now methane is a gas, right? Obviously, because you farted it out, right? Methane's a gas. So it's also combustible. So if you look on YouTube, look what everybody does with their fart. Now, that doesn't mean that you guys go and light up your farts. Don't do that, right? Because if you catch things on fire, I am not responsible for that, okay? So it is a combustible gas because it has that carbon. It can cause a chemical reaction, right? So often you don't have something right next to a dairy or a ranch that is going to have fire going constantly because guess what? You don't want to cook your cows too soon, right? We want to cook them slowly. You know, I like my steak a little rare, you know, a little bloody. You know, I don't want it well done, right?
I need it.
So methane, again, is a gas, but we need to know what methane looks like. Methane is made up of carbon and 4 hydrogens. Carbon, 4 hydrogens. That's what methane looks like. This is the structure of what methane should look like if we had a methane molecule, right? So we'll use these plastic models to sit there and represent that methane molecule. This here is the ball and stick structure. This here is called the space filling structure. And this is just a combination of all of them coming together so you can see the model itself, okay? So we will use models constantly throughout this book to represent chemicals, right? To give us an idea of what it should look like, how they're gonna behave, how to attack them in certain ways, okay? Are you guys with me? Good.
Yes.
Let's see. Okay, so we are using symbols, right? We've talked about H. H stands for what again? Hydrogen. O stands for what?
Oxygen.
So we have H and O stands for oxygen. C? Carbon. Okay, so you guys know pretty much that those symbols represent the elements that we're talking about. It makes it easier for us to write rather than having to write down hydrogen, oxygen, all the way out. We just have to write up those symbols. Makes things so much easier, right? Simple, not too hard, right? Okay, so let's start using some of the stuff that we know. We've talked about the state of matter. We know that, maybe, there we go. State of matter. We know that there's gas, there's solids, and there's liquids, right? So what is the difference between a solid and a liquid? So we know it's a physical form. Yeah, that's correct. Physical form. What else?
Isn't it like how like close together the atoms are?
So you're saying how close they are. So you're telling me, are you saying that, let's see,
Solids, they're like
they're really close together? Okay, so solids are really close together, and liquids?
not that far apart because that's
Okay, so they're a little bit apart. And then gas is like everywhere, right? Okay, good. That's good. Okay, so now I want you to think about this, right? So if it's really close together, that means it's really tight and packed together, right? Okay, so if I put ice and water, does the ice sink?
No.
Why? But if I put a brick, or let's say a solid piece of metal into a liquid form of metal, it'll sink. Or freeze ethanol. If I freeze ethanol and I put it in ethanol, it'll sink. Ethanol is drinking alcohol, right? If I freeze ethanol and I put it in ethanol, it'll actually sink. Why does water float?
Is it because the space of the molecules or the space?
Oh, somebody said
It's
something about
because of
density.
density. Mhm.
Oh, okay. That's good. That's going to bring up something else. So he's right. Ice is less dense than water, slightly less dense. The reason why ice floats and other things don't is because ice will actually put a little bit of space in between the molecules. So it's organized. And so you don't get as tight fitting as you would with other metals or other solids. Okay. So because of that, it has those gaps of air, which makes it a little less dense than water. So it'll float instead of sink. Okay. So, but what you're saying is right. Those molecules are going to become packed, right? But there's something else that happens in the case of solids. Okay, so we were talking about other differences, right? Other difference between solids, liquids, and gases. And we were kind of stuck on spacing, right? So we know that solids, all the molecules are real tight together.
Mhm.
Liquids, they're a little bit looser. And then gases, they're all over the place. How many of you guys have been to a nightclub or a dance? You guys go to dances?
Oh,
Are there dances here? Hey, I don't know. They could have fake IDs and everything. I know these guys, Okay, so no nightclubs, but you guys have been to dances, right? Okay, so now if everybody goes to the dance and everybody's on the dance floor, is it packed? Can you move? It's real crowded, right? Okay, so if the dance is kind of early, there's a little space and everything like that, and not too early, because too early, it's too much space, right? You can really move, right? You guys can sit there and do, oh yeah, you can really get down, right? You have plenty of time. Oh yeah, you can move, right? Now, if it was totally open, then you can sit there and you move your hands. You have plenty of space, right? You don't have to worry about knocking anybody in the eye, right? Okay, so when we talk about atoms or we talk about molecules, it is exactly the same thing. It's about movement. It's kinetics. Do you guys know what kinetic means?
Motion.
Motion, right? Okay, so the kinetic theory basically says that if you're a solid, you don't have a lot of room to move. You're packed, right? So you're doing this. You're doing that cute little dance. You're trying to look cute, and that's it. If you're a liquid, hey, you can sit there and get down. You can move a little bit, right? And then if you're a gas, you're bouncing off the walls, right? And you're able to move very fast. So if you think about it, how many of you guys have gone to a beach and the sand is really, really hot?
Yeah.
Okay, so do you do your cute walk to the water and or do you race to the water?
Yeah. Hop into the water.
You run to the water, right? And that's because that temperature, right? So if it was cooler, you'd be doing your cute little walk to the water, just kind of I want them to check out my new bikini, right? Okay. And then if it was cold, then you go really slow because God, I got to save my energy, I don't know if I want to get in that water. If this is cold, that water must be really cold. So you go really, really slow. So that's exactly what's happening in terms of a molecule. Low temperatures, right? You're not moving that much. You're right there, tight. You're compact. You warm it up, oh, you get a little flow going. You warm it up more, you're bouncing off the wall. Think about water. Water, when it's frozen, what happens? Nice solid cube. Is it moving?
Mhm.
Will it run?
No.
No, right? It's stuck
Right.
right there if it's cold, right? Now, if I heat it up, it becomes water. What happens? Will water pour out on the ground? Oh, it can move now, right? And then in gas, in terms of steam, right? I'm boiling water. Does steam just stay above the pot? Or does it fill up the entire room? Okay, so that explains what's happening in terms of the different states. It's kinetics, it's movement,
Mhm.
right? Let's see. Okay, so we have solid, liquids, and gases. Now, when we talk about solids, there are two types of solids. We have those that are organized. Water is an example. It's really organized. That's why it gets those little spaces so that it floats. We have others that are amorphous. Do you guys know what amorphous means? Amorphous. Have you guys, anybody watch sci-fi movies or play D&D? What is a morph? M-O-R-P-H-F or P-H. What was that? Transformation. Somebody says transformation. Something that changes shape, right? Amorphous basically means lack of shape, right? Amorphous, okay? So something that's amorphous, it doesn't have a pattern. It's not organized, right? It's very random. So solids can be in two forms. Most of them are going to be crystalline, which is organized. The other form is amorphous, unorganized. So for instance, glass, if you're not careful, will be amorphous. And then they'll cause those little breaks that happen in between. So if you don't handle glass the right way, if you don't melt it and blow it out the right way, you make it amorphous, okay? Okay, so this here, let me see if I can get this to move. Okay, this is just basically telling you everything that we just talked about, right? So gas is going to occupy the room, it's going to occupy the shape that whatever it's in. It's going to take up the volume of that entire container, right? It's going to be moving. And it's going to be moving pretty fast. Liquid. Well, liquid is going to occupy only the part that it's contained in, right? So up to the part that it's at. Its volume is going to be relatively constant. It's also going to be moving, right? Those molecules are going to be moving. And these guys are going to be kind of close, right? So their movement is going to be less than in the case of the gas. Solid is going to be very rigid. It's going to be fixed. So we get those nice sculptures, right? The unicorn or the butterfly or whatever, right? That volume is going to be constant. Those particles, they're going to be vibrating, but they're going to be moving just a little bit, like we do when we're tight in that tight dance, just kind of moving our neck, And it's going to be very, very tight. And so the speed of the molecules or the spacing of the molecules is going to be very, very close. We've already talked about physical change. Talk about it again since they didn't get to hear all the good stuff, right? So when we talk about physical change, we know that physical change makes reference to changing of state, right? So a good way of thinking about it is if you put in something and it's exactly the way it came out, so you put in water and you get water out, then, or if you put in water and you can get it back to water, then that probably means that it's a chemical, not a chemical reaction, a physical reaction, not a chemical reaction. So for instance, if I melt ice and then I freeze it back, don't I get ice again? Okay, so if I can put it back in the form that I had it, then we know that that is definitely going to be a physical change. Now, if I can't get it back, then we know that that's most likely a chemical change. How many of you guys cook? Cook, like cook food. Anybody cook? Okay, so I like to try to make candies and cookies every once in a while. And I often try to do this when I'm under a lot of stress and I have no candies or cookies or anything in the house, right? Because I have a sweet tooth when I'm stressed out. So like when I'm grading and they're failing all of the tests and everything like that, I get worked up. Either I drink or I eat, one of the two, right? Again, you can see why I picked on a couple of weight, since then. Man, a lot of people fail some classes. So hopefully you guys help me get slender by getting all A's, okay? So I try to make caramels. You guys know how to make caramels? Caramels, okay? Caramels are basically, it's sugar, butter, maybe a little bit of milk, right? And a little bit of vanilla, right? That's it. So you always start off with trying to melt your sugar, right? So you put your sugar in a pan, you put in some butter. Well, this is an example of something that I do every once in a while. I'm in the middle of grading. I forget that I'm cooking at the same time I'm grading. I start by melting my sugar. My sugar's there. It's perfect. It's all nice and white. I melt it a little bit. It gets caramelized. It starts getting that brown color, right? And then I forget totally about it. I burn the crap out of it, right? So at the end of the day, I get carbon and water. Initially, I started off with sucrose. Sucrose is table sugar, right? I'm gonna give you the chemical formula since you guys already know about chemical formulas. I'll make it easy. Okay.
But then, are they able to see it?
Yeah, they both should. Can you guys see my
We can-
C12?
Yes.
Yeah, okay, good.
Do you want me to write it down?
Are you messing with my writing? Okay.
Is it right? Yes, perfect. Okay. I'll just see. That was good.
Okay, so sucrose is C12, H22O11. Okay, so that's sucrose. That's the stuff that we eat. We put in our coffee in the morning, right? So sucrose, if we're going from sucrose to carbon, and water.
Here, I'll write it down.
Okay.
It works now.
just okay. Okay, so now on the let's see. On the left-hand side, I had to think about it. On the left-hand side, that's called our product. Okay? On the right-hand side, on the left-hand side is our reactant, on the right-hand side is our product. Okay? So, in this case, we're breaking down our product. I'm going to ask you a question. I want you to think about it really hard. Is this a balanced chemical equation? No, because we know that a balanced chemical equation means what?
The same you
Okay. Okay, I heard it. So what goes in must come out, right? And they have to be the same, right? So we need to balance this chemical equation. So you guys gonna help me balance this chemical equation? Okay, so let's see if we can do that. Okay, so I have how many carbons? I have 12 carbons. So I like to write this down here. So 12 carbons. Okay, how many carbons do I have over here?
1.
Okay, does 1 and 12 equal the same?
No.
Okay, so what do I need to do? I add a coefficient. What do I need to add as a coefficient? Okay,
12.
so I'm going to put a 12 here. So this guy, again, is called the coefficient. Okay, so that's our coefficient. So that means I have 12 carbon. Okay, so now I have 12 carbon. I'm doing pretty good now. Okay, hydrogens. How many hydrogens do I have? 22. How many do I have over here? So I'm going to put this down here. So you told me I have 22 over here. And then how many do I have on this side? On the 2. Okay. So 22 equals 2? No. Okay, so what do I need to do? So I add 11 as a coefficient. Okay. So that gives me 22, right? And then let's look at our oxygens. Thank you so much. We have 11. And then over here on the product side, we have 11 because we multiplied that. Okay. So perfectly balanced. Man, look at that chemistry. That's chapter 8, right? Simple. Not too hard. Excellent. Okay, but the key is, there's a key here, right? This here is a chemical reaction. It is not a physical reaction. Why isn't it a physical reaction? Because we're changing it, right? So we have something that's all together and is being broken apart, right? Simple, right? Excellent. Okay, let's see how good you guys are then. Okay. Let's see. Okay, maybe I can get this to work. Oh, hold on. Okay, let me clear. Okay, so A, log burning. Is that going to be a chemical reaction or a physical reaction?
Chemical.
A log burning. Okay, good. Okay, so we have a dispute going on here. I have some people say physical, chemical, right? The A log burning. A. Everybody's looking at A, right? A log burning. A log burning. How many of you guys raise your hands and at home? You can put thumbs up if you believe it is a physical reaction. If you believe it's a physical reaction, raise your hand. Raise your hand high and proud. Okay. How many of you guys think it is a chemical reaction? Raise your hand. Okay, the correct answer is chemical. It is a chemical reaction. Think about it, right? A log burning. First, you have wood. At the end of it, what do you have? Ash. Is that change?
Yes.
Can you make wood back from ash? If
No.
you can, let me know, because you must be something special, right? I have some other things that we got to work on then, okay? Okay, B, an icicle melting. How many of you guys say that's physical? Raise your hand.
Physical.
How many of you guys think it's chemical? Raise your hand. Okay, good. It is a physical reaction or a physical change. Okay, how many of you guys use glow sticks? Glow sticks. Glow sticks, right? Ray party. Okay. Now, if you crack open that glow stick, is that a chemical reaction or is that a physical reaction?
Chemical.
Okay, how do we know? Because we got that change and eventually it dies. Does it work afterwards? Oh, after it's gone, right?
Yes.
Are you sure? I think somebody told you a lie on that one. Yeah. Okay, we'll test it out. Don't worry about it. I have a couple of experiments planned. Okay, so we know that case, the glow stick is a chemical reaction. Simple, right? Not too hard. God, chemistry is so easy. What was that? Oh, me? Yes, that's exactly what happens. It just... Okay, let's see. Still struggling there, Jess. I got to get used to it. I got mine working, but I don't want to change midway. Okay, so now we're going to be talking about if something is pure or if it's a mixture. Okay, how many of you guys have been to a diner? A diner, like Denny's and, okay, back in the old days, Denny's used to have the sugar in a little jar, you know, and a little Spencer, and then they had the salt and pepper there too. They didn't have them individually packed like they do now, right? So that's in the old days. Do you know why they stopped putting them, or why they start individually packing them? Well, what was that?
Overuse of it.
It is easy to switch. So when I was a kid, I used to love going to diners, and you'd open up the sugar and you pour the salt in, right? Can you tell the difference? Right? Okay, so, but I have salt and sugar, right? And I'm putting salt and sugar. Salt tastes what? Kind of
Salty.
bitter? Salty, okay? Salt tastes salty, okay? Sugar tastes,
Sweet.
okay. Now, if I mix them together, do they taste the same?
No.
Are they different?
Yeah.
Okay, so is that a pure substance or is it a mixture?
Mixture.
But it looks alike. Does it look alike? Doesn't salt
They
look like
do.
sugar? Can you tell them apart by looking at them? No,
No.
you can't, right? So when we have mixtures, we have to define what a mixture is. If something looks exactly alike, like salt and sugar, right? That's called homogeneous. Homogeneous, like homogeneous milk, or homogeneous. I'll spell it for you. Okay, homogeneous. Yes, ma'am. You had a question? Go ahead. Okay, so homogeneous basically means the same, right? So you guys are familiar with homosexuality. Means that you like the same sex, right? Same. So you think about homogeneous, anytime you see HMO, it means the same. Homogeneous, the same. Heterogeneous. So heterogeneous is, wouldn't say opposite, or we could say different, right? Because it's not necessarily opposite. So it's kind of like putting salt and pepper together, right? You can tell the difference between salt and pepper. Okay, so those are two types of mixtures. So we either have something that's pure. If it's just sugar, it's pure. If it's salt and sugar, it's what type? Homogeneous. Salt and sugar. Okay. And salt and pepper. Okay, simple? Good. Okay, so let's talk about this, right? Okay, so if I have water and then I have salt water, how many of you guys cook pasta? Have you noticed food is a big part of everybody cook pasta? Why do you add salt to pasta? I mean to water, to the water itself.
So the noodles won't stick.
For the flavor.
Okay,
So the noodles
somebody
won't
said,
stick.
I heard the flavor. That's all I heard. Flavor. What else? Oh, he says the water evaporates faster. Okay. Anything else? No, nothing else? What do you think? Okay, it boils faster. So we have evaporates faster, it boils faster. I think that's pretty much kind of like the same, right? Okay, what do you guys think at Fireball? Yeah, so we have people at Fireball. We have people in Kalinga. We're universal, right? Next year, we're going to try New Mexico. I'll take a trip there every week, once a week. Okay, so let's talk about this. So here's an example, right? Yeah, let me see. Maybe. It just does not want to behave there, Jess. Okay, there we go. Okay, so this is temperature versus time. This is a solution with salt. So it's basically water and salt. This here is just water. We know that water boils at what temperature? It boils at 100 degrees Celsius. It freezes at 0 degrees Celsius. That's something you want to keep in the back of your head. It's really important to know, especially if you're going to go to the Midwest. Okay, so if you look at it, somebody says, oh, it boils faster, right? Actually, what happens is, by us adding salt to water, it causes it to boil at a higher temperature than 100 degrees Celsius. It actually starts boiling about at in this case, it'll be about 105, 110, somewhere in there, instead of 100 degrees. So if you're cooking pasta, right, you throw your pasta in. If the water is hot enough, it cooks the pasta better, right? Faster, so it doesn't get soggy. How many of you guys like soggy pasta?
No.
Exactly. That's why we put the salt in there, to keep it from getting soggy, right? Okay, so how are we doing on time? Doing great on time. Okay, so we know that it's also going to speed up that process. In other words, it's going to actually get temperature to a higher temperature faster, and it also gets to a hotter temperature. Are you guys with me? Because if you're not talking with me, you're talking against me, and I don't like that. You guys understand? Got it. Okay. Now, let's talk about those mixtures again. Let's see how much you guys know. Okay, so if I have a pure substance, if I have pure bromine, is that homogeneous? Is it heterogeneous? Or is it just pure?
Pure.
Just pure.
Pure.
Now, if I have water, is that homogeneous? Is it heterogeneous? Is it homogeneous? Or is it just pure?
Pure.
Pure twice.
Homo.
Pure water, right?
Okay.
Okay, so if I mix my bromine and my water together, I have more bromine than water. Is that homogeneous? Is it homogeneous, heterogeneous, or pure?
Hetero.
Heterogeneous.
Okay, so this is what it looks like. Can you tell the difference
Yes.
in that case?
Yes.
So you can tell the difference between water and bromine? Yes, ma'am. Yes, ma'am. What was that?
Like you're not gonna be able to see which part is that one and which part is the other one because they're mixed.
Okay, so let me ask you this. So if I have Coca-Cola, and I have Dr. Pepper, right? And I put them in the same cup. Is that going to be homogeneous or is that going to be heterogeneous?
Hetero.
Okay, here's a good one. If I have milk and orange juice, yeah, it's going to be heterogeneous. Try it.
Mm-hmm.
Tastes delicious. Creamy orange juice? You never had creamy orange juice? Oh, it's delicious. Add a little sugar. Actually, if your orange juice is sweet enough, you don't even have to add sugar. It's like a creamsicle. Have you guys had a creamsicle before? You never had a creamsicle? You guys are missed out on the best thing in life.
Oh, you know what?
Creamsicle.
The thing that has the orange from the outside and then it has
The cream on the inside, right? Yeah, see? Exactly. Yes. Okay. So, are you guys clear? So, you guys understand the difference? Okay, good. It is homogeneous, and both cases are homogeneous. Only thing, one is just going to be lighter than the other, right?
Mm-hmm.
You're doubting me? Yeah. If you have questions, hey, it's okay. It's okay. I am not perfect. If you doubt me, ask me. I'll let you know, right? Okay. No, if you have questions, really, seriously, I'm just messing with you. But if you seriously have questions, because if you don't ask questions, I'm going to assume you know it. That means it's going to be on exam that much faster. And your first exam is next Friday. It's going to be, well, technically it's going to be due next Friday, right? You see? So you'll actually have, I'll see you guys on Thursday, but it'll be due on Friday. You guys understand how that works? I will be online tomorrow, but I'll be here on Thursdays. Tuesdays and Thursdays, I'm physically here. Homogeneous basically means the same, so it looks the same. So all it is that mixture looks exactly the same. Heterogeneous basically means the mixture visually looks different, like salt and pepper. You guys get that?
Yes.
Mm-hmm.
Okay, good. Okay, let's see. Okay, so this is basically the official definition, right? Homogeneous, uniform in appearance, uniform in properties throughout. Okay. Heterogeneous, heterogeneous, non-uniform composition, visible different phases. So if I put dirt and water, is that homogeneous or heterogeneous?
Homo.
Okay. Because what happens when I shake it up, it all looks like it's together and then it all floats out, right?
Yeah.
So that would be hetero, right?
Oh yeah.
Okay.
Yeah. Hetero.
Okay, so if I'm making a cocktail, right? And I'm having vodka with the water back. Vodka is clear. Water is clear. So if I mix them together, is that pure?
No.
Or is it
Homogeneous.
homogeneous? Okay. Okay, so now the thing about mixtures. Okay, so if we have mixtures, we can use physical methods of separating those mixtures. Like for instance, if we have, let's say, iron and sulfur, right? Iron and sulfur mixed together, we can sit there and use a magnet because we know that iron will do what with the magnet? Iron is magnetic. It'll actually bind to the magnet, right? So I can clear out all of the iron from that sulfur, and then I'd have pure iron, and I'll have pure sulfur, right? Yeah? Good. So we can also use other methods. I would normally say you guys are young, so you better not be making alcohol. But in terms of making alcohol, right? So if I want to make alcohol more concentrated, how do they do that?
More alcohol.
Well, they use yeast to make alcohol, right? That makes it to a certain concentration. Usually yeast make it about 20, at most 23% alcohol, right? So if they wanted 100 proof or 200 proof, right? 100 proof basically means it'll be 50% alcohol. 200 proof means it's 100% alcohol. So if I want to make it 200 proof, how am I going to get that alcohol separated from the water?
Yeast.
The yeast is just a catalyst. It does the work to make it. That's all it does. It's not getting rid of the yeast, right? So if I want to get rid of the water,
Water.
there's no filter that's going to be good enough to separate water and alcohol because they're not exactly the same size. They're a little bit different, but you can't get a filter that fine to sit there and separate them. So you're not going to use a filter, but that's a good thought, though. It's an interesting thought. Any ideas? Okay, tell me something about that. You have water on your desk. Tell me about that water. It's tasty? Nothing like water. So why are you using? Why don't you use the water that's coming out of the sink? Are you too good? It's filtered? Oh, so filtered is one way, but there's also something else. What is the other way that you can get it pured? What was that? Distill it. Oh, distill it. What does distilling mean? How? Oh, wait. Somebody said boil it. Yeah. So guess what? What happens when you boil water?
Evaporates.
It evaporates, right? So in the case of when you're trying to clean up water, you're usually having stuff that isn't going to evaporate, right? A lot of it'll be solid, right? So if you boil the water, it'll make steam. The steam then can be collected, and then you can cool it down to sit there and make it pure water. Well, you can do the same thing with alcohol, right? You can boil a mixture of water and alcohol. Water boils at 100 degrees Celsius. Alcohol boils at 89 degrees Celsius, right? So long as you don't go up to 100, your water isn't going to come up. Your alcohol is, right? But the problem is, so again, don't do this at home, right? Yes. So basically what they'll do is they'll run water on the outside of the pipe. So they'll let the steam come up. They'll put a U pipe in, so the steam will go through that pipe, and then they'll run water down that pipe, and then they'll collect it. I'll show you an example here in a second, right? Okay, so now again, don't do this at home because most people blow themselves up when they try to distill alcohol because they don't know how to do it right, right? And what happens is because alcohol is also flammable, right? So if you get up too high, just a little bit too high, whoosh. You'll hear, particularly in the country, there's a lot of people in the country that try to make their own alcohol and they end up blowing themselves up. Okay, so one way is distillation. I'll show you an example. The other way is something that you had mentioned. You mentioned filtration earlier. Filtration is another way of doing it. Okay, so this here is an example of distillation. So if you take a look here, the liquid is being boiled in that flask. Now, that flask then goes, it evaporates. You have this little thermometer up top. It goes down this tube. It gets cooled. So they have a cooling tube that runs water on the outside of the pipe. It cools down the liquid, and then you get your pure, in this case, pure water, right? Pretty simple. Nice little system. This here is filtration. You put a filter. How many guys make coffee? Every day, right? Okay, you got a coffee filter. You put your coffee grinds in the top and you just run water through. Do your coffee grinds go into your coffee?
No.
No, right? Okay, so this is exactly the way filtration works as well. Simple. Okay, so now when we think about that separation, right? So we're separating two mixtures. Now, when we do a chemical reaction, we could separate elements on a periodic table from a compound, right? So definitions, an element. Elements are basically what we see on our periodic table, right? Oxygen, carbon, right? Hydrogen, right? All of those are considered elements, right? They can't be broken down to anything smaller. They can't be broken down to another smaller element. That's it. That's all you get, okay? Compound. A compound is two or more different elements. So, based upon that definition, H2O, is that a compound?
Yes.
Okay. A molecule is two or more elements. Is this a molecule?
Yes.
Okay. What about, let's see. Let me see if I can get this. Oops. Hover. You said hover. I'm trying here. Okay, what about this? Oops. Okay. Let's see it. I'm better with the mouse. If I can find the mouse. Okay, there we go. Okay, is that a molecule? What is the definition of a molecule again? It has two or more elements. Does that have two or more elements?
Yeah.
It's a molecule. Is it a compound? No, it's not a compound because it's not two different elements. Do you see the difference? Yeah, no, maybe. No? So we're talking about a molecule, compound, and element, right? So in the case of a molecule is two or more elements. Real simple, two or more. H2, is that two or more? Yeah. So that means it's a molecule, right? H2O, is that two or more? So H2O is a molecule. Now, a compound is two or more different elements. Okay, H2O, is that a compound? What about NH4 plus?
Oh gosh. Okay,
NH3. Is that a compound? Is it an element? Is it an element?
What is element?
Pure, right? Pure can't be broken down to anything else.
Mhm.
Right? So I could break NH3 down into N and H2, right? Okay. So can you pull up the periodic table, P table, please? So that kind of brings me to some special elements. We kind of talked about this yesterday. That term diatomic. You guys remember us talking about diatomic? What does di mean? Two. Oh, you guys are prepared. I like this. Two. Okay, mono means?
Mm.
Okay, so if it's monoatomic, it means one atom.
One atom.
Diatomic means two atoms. Polyatomic.
Many.
Poly basically means more than one, more than two, right? Okay, so we have more than two, it's called poly. How many of you guys drink beer? Oh, okay, wait. See, I was waiting for, I see, she was smart. She's like, none of us, because none of us are of age, right? Good answer. But he raised his hand there earlier, right? He just ratted himself out. Okay, so I'm going to give you guys a mnemonic because one day you may want to try beer. One day, right? One day, right? Okay. Have no fear of ice cold beer.
Again.
So
the
we said
ice cold
the
beer,
mnemonic is what again?
have no fear of ice cold beer. Hydrogen, nitrogen, oxygen, iodine.
Okay, so cold, chlorine, and beer, bromine. Where's your mass? Yep, it's chlorine. It's not carbon. Yeah, it's chlorine. Okay, you guys got that? Simple? Bromine. Br. Bromine.
Oh, I'll write them down for you guys. You're welcome.
Okay, so we know that these are diatomic. So if I'm talking about oxygen gas, what am I going to write for its chemical formula? O2. If I'm talking about nitrogen gas, what am I going to write it for its chemical formula? Okay, so if I'm talking about nitrogen monoxide, nitrogen N and monoxide mono
Mano?
one N NO no, right? No, nitrogen monoxide. Okay, so Now, N2, is that a molecule or is it a compound? N2. How many people say it's a molecule? How many people say it's a compound?
Compound.
How many people say it's a diatomic element? So is it an element? Okay, because it's only nitrogen. It's a diatomic element. Okay, now if I have NO, is that a molecule? NO? NO. Is it a molecule? What is the definition of a molecule? Two or more elements. Does it have two or more elements? It does. Nitrogen and oxygen. That's two, right? Okay. So it is both a compound and a molecule. Is it an element? Nope. Okay. Pretty simple, not too hard. So we've talked about elements, we talked about compounds, we talked about molecules. Are you guys feeling comfortable? Are you happy? It's all right. Still not going to make you happy. We got more stuff to learn. Okay, so if we think about mixtures, hey, don't get too happy yet. We ain't done. We got a long way to go. Okay, so we think about mixtures. Mixtures can be broken down into different compounds because it's a mixture. We can get alcohol and water if we wanted to, right? Okay, so mixtures can be broken down into compounds. They can also be broken down into elements or a combination of both. Now, a compound, a pure compound, can only be broken down by chemical means into those pure elements or other compounds. So a mixture can be done by physical means. Okay, you guys are clear on that, right? Okay, so these are examples of the first one here. These guys here are all examples of elements. On the other side, we have examples of compounds, right? So a lot of things that you guys run into, baking soda, right? Compound, sodium bicarbonate. The lead in your pencils, that's graphite, right? That's just carbon. Your pennies, right? Copper. Chalk, calcium carbonate. Okay? So we've already talked about the symbols. You guys know that if you look on a periodic table, you either have, and it's really important, this is the important part of writing your symbols. When you're writing your symbols, you always have one of the letters has to be capital. If it's only a single letter, it's going to be capital. If it's two letters, the first letter is capital, the second letter is lowercase. You don't want to mix that up because you're going to be telling me something different. So like for instance, if I tell you PO, right? And I write it like this, so what does that tell me? Is that phosphorus oxygen? No, it isn't. What is it? Oh, you guys don't have the
They don't
nice
have the-
periodic table. Oh, we got to hook you guys up with a good periodic table. It's called polonium, right? Polonium. Okay, so if you write PO and you were talking, you really meant to say capital P, capital O, and somebody had polonium instead of PO, you can cause something to blow up, right? So you want to be sure to write it correctly.